We've touched on how we can write a script in Python on a Windows computer and then run the same script on a Linux computer, or vice versa. This is the case for scripts written in many other interpreted languages too. So you might be wondering, what's an interpreted language? Well, when you want to run a program written in traditional programming language like C, the source code is fed into a piece of software called a compiler. The compiler translates this code into machine-level language, which means a language specific to the underlying architecture of the computer it's running on. The computer can read and execute the machine-level code directly. This makes compiled programs super fast to run, but the compilation process itself can take a bit of time. Some examples of commonly used compiled programming languages are C, C++, Go, and Rust. On the flip side, programs written in an interpreted language generally rely on an intermediary program called an interpreter. These programs use interpreters to execute the instructions specified in the code, rather than running them through a compiler first. So, this makes the development cycle for a program written in an interpreted language much faster, because the developer doesn't need to wait for the code to be compiled to execute it. And the same code can be read by interpreters running on different operating systems without needing to make any additional changes. The trade-off is that interpreted languages generally run slower than compiled ones. Python, Ruby, JavaScript, Bash, and PowerShell are all examples of interpreted programming languages. Last up, Java and C# are languages that use a mixed approach. The code needs to be compiled first, but it gets compiled into intermediate code. This means that instead of getting compiled into machine language that's specific for the current operating system, it gets compiled into portable code that can execute on different platforms. We execute this code using a program that's OS specific, the Java Virtual Machine for Java, and the Common Language Runtime for C#. Say, for example, you have a program that's written in C and you're running on Windows, but you want to run the program on a Linux server. To run the program on a different operating system than the one you're currently running on, you need to compile it on the destination OS. So, in our example, that would mean you would need to compile the source code in Linux OS, and preferably one that has the same versions of the installed libraries on the destination server. You could run the program source code in Python instead. If you did that, it wouldn't matter if you're running on Windows, Mac OS, or Linux. You could write and test the program locally and then just copy the script to the server and use it as is. The Python interpreter itself is a compiled executable that's platform specific. But once you have it installed, you can run your scripts everywhere. Okay, we've chatted a bunch about running Python scripts. Seriously, we've been talking a lot. I think it's about time we start doing, don't you? Okay, ready to see what our Python scripts can really do? We can run Python programs in several different ways. In this course, we'll focus on running scripts from a command prompt. And because our Quick Labs instructional environments will use Ubuntu, we'll concentrate on using a command prompt in a Linux-based setting. That said, with a little tweaking, the techniques we use here can be applied to other platforms like Windows or Mac OS. As we called out in our installation videos, the command to run the Python 3 interpreter might be Python or Python 3, depending on your platform. In our examples, we'll always show Python 3 because that's the command for the Ubuntu distribution we'll be using. You should use the right command for your platform. As we saw in our installation videos, when we run the Python 3 command, we get an interactive interpreter. When we run this command, it prints a bunch of things. First, we're told the version of Python interpreter we're running. Then, we get some extra information like which compiler was used to build it, and then some suggestions for commands that we can use to get more information. Using the interactive interpreter, we can do everything we learned in the introductory course on Python. Like say, printing hello 10 times because, Python's always down to have a convo. Hey Python. So this is fun and useful for experimentation and trying out new concepts, but unfortunately, we can't save any of our work. Once you close the interpreter by typing exit or pressing Ctrl-D on Linux and Mac OS, or Ctrl-Z on Windows, the code we wrote isn't even saved. Boo. To make our code more permanent, we can store it in files. Saved Python scripts usually end with a .py extension, such as helloworld.py. Let's have a look at our helloworld.py file using the cat command, which is a command that shows the contents of a file on Linux. To run a Python script saved on a Windows system, you can just type the name of your script and the operating system will recognize it's a Python executable from the file extension. On Linux and Mac OS, you can execute the script by calling the Python interpreter followed by the name of the file. So here, the Python 3 command, the same Python interpreter as before, reads the contents of helloworld.py and then tells the computer to execute the instructions in that file. But typing Python 3 each time you want to run your script can get really old really fast. So, pro tip, there's a way we can avoid this. We can add the extra line to our file called shebang, which tells the operating system what command we want to use to execute that script. Let's try this now. First, open the file in an editor. For this example, we're going to use Nano, which is one of the editors available on a Linux system. Now, we'll add our magic line at the beginning of the file. This line tells the OS that we want to run this script using Python 3. It looks like this. And that's it. We can now exit Nano by pressing Ctrl-X, then saying that we want to save the file, and then accepting the proposed name, which is the same name that the file had before. All right, our system now knows it should execute the file with the Python 3 interpreter. There's one more thing we need to do to run the script directly without having to call the interpreter every time. We need to make that file executable using the chmod command. Remember that this command lets us change the file permissions. A file's possible permissions are read, write, and execute. To run the file directly, we want our file to be executable. This is how we do it. Marking the script as executable means that we can now run the file by just prefixing it with a /. Because the script has been marked as executable and the path to the interpreter is specified on the first line, the operating system will run that interpreter and pass the name of the script to it. This means that running ./helloworld.py is equivalent to Python 3 helloworld.py. This approach works exactly the same for both Linux and Mac OS. Maybe you're wondering why we need to prefix the script with a / instead of just writing the name of the script. The reason for this is that the script isn't located in any of the directories listed in the path variable. This variable tells the operating system where to find programs to execute. The dot in the ./ expression represents the current directory. So we're basically telling the OS to find the script in the current directory and then execute it. So we just created our first executable Python script. How cool is that? Now it's your turn to do it. Take some time and experiment with running scripts locally on your machine. We went over a lot of info in this video that's super important to get down. If there's anything that doesn't quite click yet, watch this video again and practice the scripts a few times. After that, we've got something even more exciting coming up. We're going to create our own Python module. Okay, got Python installed on your computer? Check. Got it running locally? Check. Created your first executable script? Double check. You're doing great. Let's keep going. In programming, we often reuse code that we've written or someone else has written. This is called code reuse, and nearly all languages provide some way of doing it. We talked about code reusability back when we first looked at functions. Functions let us group code into logical blocks that can be executed at a later point and as many times as we need. But as our scripts get bigger and more complicated, we want to be able to reuse more than a single function. We might even want to reuse entire scripts in other programs that we write. Let's say that you created a script that emails a daily summary of tickets you completed to your manager. The script has two main jobs. First, it assembles a list of the tickets you've closed by interfacing with the company's issue tracking system. Second, it uses that list to create an email and then sends it off to your manager. In a separate project, let's say that you'd like to automatically parse a system log and search for an event inside of it. If the event is found in the log, you want to trigger an email to notify yourself. Can you spot the functional overlap in these two scripts? Both of these automation projects need to send an email message. The most straightforward way to do this is to duplicate the email sending code, copying it from one Python file to the other. On the whole, this seems pretty easy, but duplicating code in this way has some ugly downsides. First, every time you need to make a change to either script, you have to remember to do it to both places. That means you'd have to do any update and bug fixes twice. Ugh, no one wants to have to do that. And on top of this, if your coworkers want to use the same email code you wrote for their own projects, they'd probably have to go and create new copies. As you can imagine, keeping track of all the places it's being copied to quickly becomes tricky, and so does sharing different versions. So, instead of going crazy trying to maintain a bunch of different copies of the code, we can put the code we want to reuse into a separate module. This way, we can have our scripts and our colleagues' scripts import our code without having to create multiple copies. Great, but first, we need to create our own Python module by putting the contents that we want to be part of the module into a separate file. To use the module, we'll import it using the file name. We can access each function, class, and variable defined in the file by using dot notation. Let's see this in action. We have a file called areas.py, which contains functions to calculate the area of different geometrical figures. We can see the contents of that file using cat command. We have three functions defined in this module. The circle function uses the math.py constant. That's why we import the math module at the top so that we can use it. Okay, we've seen that the functions are defined in the areas.py file. To use them in an interpreter or a script, we can import the module by typing import areas. Let's do this. Perfect. We've now loaded the areas module and can use it to calculate areas. Let's calculate the area of a triangle and a circle to test this out. Our areas module is pretty small and simple, so it fits nicely in just one file. In some cases, the code we're working with can become more complex, and it might make sense to split it into submodules. In this case, we'd create a directory with the name of the module and separate .py files for each of the submodules. To see what we mean, let's look at a list of files shipped by a module installed on this computer. The request module using the ls-l command. Ugh, this module is super complex, so all the things it does are split into separate files. Notice the init.py file. This is a special file. It's read when the module gets imported, and it's used by the interpreter to check if a directory with Python files should be a module. So, if you have a module that's split into separate files and you want the interpreter to recognize the directory as a module, you'll need to create the init.py file. Even if you don't have anything to put in this file, you need to create it. You can leave it empty, but it needs to exist for the interpreter to recognize the directory as a Python module. Wow, that was a lot of stuff to grasp. But now we know how to create our own executable files and modules. It's a little complex, so don't worry if you feel a little shaky on it right now. We'll keep practicing these concepts until you can do them in your sleep. When you start writing your own scripts, you eventually come across these websites that mention IDEs. This term stands for Integrated Development Environment, and usually refers to a code editor with some handy extra capabilities that make writing scripts a lot easier. We do most of our programming work in code editors and IDEs, so it's important to find one where you feel most comfortable and productive. It's a good idea to invest some time now in getting to know a few editors and IDEs to find the one that you like best. There's a bunch of different editors out there. Some have only a few additional features while others have a lot. One of the most basic extra features in code editors is called syntax highlighting. This means that the editor recognizes the language we're writing our code in and highlights the pieces of code that make up the syntax of the language. Let's take a look at this in a text editor called Vim, which is available on Linux. Vim includes syntax highlighting. So if we open the areas.py file that we showed earlier inside Vim, we'll see that the code includes colors highlighting the syntax. We can see that reserved keywords like def or return are shown in one color, while the names of the function are in a different color, and even numbers are in another one. To exit Vim, type :Q. Another common feature offered by code editors is called code completion. Let's check out the use of this feature with a different editor called Atom. Here we have our areas module open in Atom. We see that it also uses syntax highlighting. The colors are different, but the idea is the same. Now let's write a new function called donut, which will calculate the area of a 2D donut as the difference between two circles. Donuts. When I type def, the editor tells me that this is a keyword to write a new function. After typing the name of the function, I write the opening parentheses, and the editor knows that there will be a closing parentheses, so it writes it for me. After defining the function, when I press enter, the editor knows that the code needs to be indented to the right, so it automatically positions the cursor right there. Pretty helpful, right? Now, when I type ret, the editor suggests that I may want to type return. It's like it's reading my mind. By pressing tab, I accept the suggestion, and so my ret gets completed to return. Nice. Let's save with Control S and close our program with Control Q. And that's the power of code completion. When you need to write a lot of code, having an editor automatically complete the names of the variables and functions can save you a load of time. How you write source code depends on your personal taste, your preferences, and the applications available for your platform. You can go with whatever is already installed on your computer, like Notepad, text editor on Windows, TextEdit on macOS, or Nano on Linux. You can choose a more advanced code editor like Atom, Notepad++, or Sublime Text, or go for a fully featured graphical IDE like Eclipse or PyCharm. Once you've found your favorite one, it's a good idea to take the time to familiarize yourself with the editor's capabilities so that you can get the most out of it. Feel free to experiment writing some scripts and executing them until you feel comfortable editing your Python scripts. Now, a word of caution. As an IT specialist, you don't want to be completely tied to just one editor. It's possible you may need to debug a problem on a computer with a different editor installed, and you don't want to waste time installing your preferred editor. So, make sure you have a basic idea of how to use an editor that's installed by default on the computers you work with. Graphical code editors with additional capabilities like Atom or Eclipse are pretty nifty and can save us a lot of time. But you should also learn your way around at least one command line editor like Vim, Emacs, or Nano for the times you might not be able to use the graphical editor. For example, you might need to connect to a remote server that's running on the cloud, where you won't be able to use a graphical editor. We've talked a lot about setting up your environment, and you can now write and run your own Python scripts and Python modules. As an IT specialist, thoughtfully applied automation can play an important role in your work. Look at automation like an IT force multiplier, a tool that can increase the effectiveness of an IT team without needing to increase the number of team members. In other words, automation can allow the IT infrastructure to scale, keeping pace with growth and demand. Scalability means that when more work is added to a system, the system can do whatever it needs to complete the work. For example, think about the impact on IT when a company hires a new employee. New employees might have to access a range of technology resources to do their job. Onboarding tasks can include creating a user account, a mailbox, and a home folder, and setting up the appropriate permissions to control access to various systems and resources. If the company doesn't hire a lot of employees over a given period, someone could manually do these tasks each time a new person is brought on board. Although I'm willing to bet that that will get tedious real fast. But as the number of new employees increases, so does the time it takes to set them all up in the system. If a company hires 10 times its usual number of new employees in a week, the IT person in charge may find themselves performing nothing but the new employee account setup and going crazy at the same time. They would probably have to put a bunch of other projects on hold until they've set up all the accounts. As a human, they may also make some mistakes during the provisioning process, like misspelling a name, forgetting a step, or giving a user account the wrong permissions. They then have to fix these mistakes, which means even more work. Yikes. Now, imagine if the company continues to hire at this pace. They might need to assign another IT specialist to pick up the work that's being neglected because of all the new accounts to set up. Or there might be so much to do that 2 IT specialists might need to be assigned to the account setup. Basically, this doesn't scale well in terms of financial resources, mental investment, or reliability, especially if the company continues to grow. What happens if the rate of new hires doubles, triples, or grows even larger? Throwing more people at the problem quickly becomes impractical. Okay, so assuming that we're all on the same page about how manual onboarding has its issues, let's think about how we can improve the process with automation. Well, instead of having one person interact with each separate system to create a new user account, a mailbox, a shared folder, and permissions, it'd be more efficient if the IT specialist could write a script to do all of this. We could then have a computer do these tasks each time a new employee is hired. When given initial information, like the new employee's name and job function, this script could carry out each step automatically, so humans would only need to intervene if a task failed for some reason. The computer would execute each step in the script and in the given order, and in exactly the same way. It would never need to deviate from these instructions. We could even improve the script further. Instead of having the IT specialist enter a new employee's information into the script each time it's run, the script could just read the data from a company's human resources system. That will make the entire workflow begin automatically on the employee's start date. In this example of automation, we've made a repetitive, time-consuming task faster and more reliable. We've also freed up human resources, allowing IT specialists to focus on more strategic or creative work. Another subtle but super helpful benefit of automation is centralizing mistakes, which means if you find an error in a script, you can fix the error once and for all, which isn't the case for mistakes made by humans, of course. Hopefully, you're now even more sold on the benefits of automation than you already were. But, as we've said before, automation is not a fix-all. If badly executed, automation can cause as many problems as it can solve. To avoid that, we need to know how it can go wrong. So next, let's check out some ways automation can fail. Hands down, automation makes our lives a lot easier. But despite its many benefits, when automation is implemented without thoughtful design, it can cause some serious problems. Let's take a look at some ways that automation can fail and what we can do to avoid them. Any task or process we automate comes with a trade-off. Is the time and the effort it'll take to write the script worth the potential automation benefits? A simple heuristic that can help us decide is to estimate how long it takes us to do a certain task and then multiply that by how many times we perform that task in a given time window. If we estimate that it would take less time to automate the task than it would to do it manually, chances are it's a good candidate for automation. So, if the time to write the automation is less than the time to perform the task, multiplied by the amount of times you do it, then automate the task. Let's check out a real-world example. Say you generate a daily report on your system's usage, and it takes you 5 minutes a day to do it. If automating this task takes you 1 hour, then in 12 days, you've already saved the 60 minutes it took you to create the automation. This would be a great use of your time, as it would free up those 5 minutes every day to do something else. If instead it takes you 10 hours to create the automation, then it would require 120 days or 24 working weeks to start saving time on the task. That's almost 6 months until you'd start reaping the benefits of your automation. It's even possible that by then, the requirements for the report will have changed, needing even more of your time. Usually, the decision of whether to automate or not isn't so straightforward. If a task is complex and performed infrequently, it may seem like automating is more trouble than it's worth. But keep in mind that once a task is wrapped in automation, anyone can do it. It can be very useful to automate a complex, error-prone task if it's critical that the task be done correctly, even if it's not executed that often. There are no hard and fast rules on when to automate, but the cost-time trade-off can help guide your decisions. A concept called the Pareto principle can also be a useful guideline to help you decide which task to automate. When applied to automation in IT, the Pareto principle states that 20% of the system administration tasks that you perform are responsible for 80% of your work. If you can identify and automate those 20% of your tasks, you could save yourself a whole lot of time. It's tricky knowing when it's best to automate, and automation that's been implemented can be fragile. If underlying systems change and the automation isn't updated accordingly, workflows can break. Imagine an automated backup system that periodically saves the contents of a sales database. Let's say the automatic backup program uses a disk identifier like dev SDA1 to know where the data to be saved is stored. What happens if a new disk is added to the server and the disk identifier changes to dev SDB1? The automation will no longer be able to access the disk it thinks it should be backing up, and it will fail. This process of software falling out of step with the environment is sometimes called bit rot. The actual bits in the script don't really decay, it's the assumptions about the implicit signals the script relies on that rot. It's important to think about how your automation will handle errors. Automated systems perform actions without human intervention, so it's easy to set and forget them. If an automated system fails and it goes unnoticed, the consequences can be really bad. Let's revisit our backup example. Imagine that the backups fail because the disk identifier has changed and no one notices. Sometime later, the sales database server crashes and the data needs to be restored. The IT specialist will be in for a nasty surprise when they discover that the automated system hasn't backed up in a while. False confidence in an automated system may also factor into decision making. For example, if the database needs to be upgraded, system administrators may be more willing to proceed with a potentially risky operation, since they believe they can recover the data from backups. So, how can we avoid these silent failures? You can build a method of notification into your automated systems. This way, if the automation fails, a human is notified and can investigate. This notification method could be an email, a new entry in the internal issue tracker, an update to a dashboard, or even a page to the person who's on call for the service. Whichever the method, it's important that the notification services the error so that a person can fix the automation. Worse than automation failure, though, is when automation succeeds but performs the wrong action. To build on our earlier example, what if the backup system was correctly performing its task but was configured to back up the wrong data? A restore of the incorrect sales data could lead to data loss or even data corruption, where customers might get charged the incorrect amount or billed for products they haven't even purchased. Oops. Sometimes a task completes, but it completes incorrectly. For this more subtle class of failures, we can use periodic tests to check in on the behavior of your automated systems. In our backup system example, we could schedule a regular restore of data from the sales database, and then check that the restored data is what you expected would be backed up. This testing process could be automated too, with scripts written to schedule the restore and to compare the data against some master dataset. Again, if any part of the restore process fails, the automated system could halt to prevent further data corruption and send a notification to a human who could investigate the problem. Along with flagging problems, good automation will make debugging easier by logging the actions it takes. The system log can be an extremely useful source of information when you're investigating an issue. We say that it's of forensic value. Our scripts can also be configured to write to the system log. Doing this creates an audit trail of useful troubleshooting information, which can help with the debugging process. Automation is an incredibly powerful tool that saves time, reduces mistakes, and facilitates growth and scalability. But we need to apply it thoughtfully to avoid some of the pitfalls that can arise from its use. Keep these things in mind, and automation can be a valuable asset in your toolbox. So, we've talked about the benefits of automation and the things we need to be prepared for. Let's now look at an example of something we can automate using Python. Say, for example, that you wanted to check the health of your computer. This can call for a lot of different checks. Verifying that there's enough disk space, that the processor isn't overloaded, that it has the latest security updates, and that it's running the services it's supposed to. To verify all of this, we need to know how to check each of these values. And of course, we'll do it by using some of the handy modules available to us. For example, we can use the shutil module and the disk usage function to check the current available disk space. Let's try it out in the interpreter. We'll start by importing the shutil module. Then, get the disk usage. Let's print the variable and see what's in it. Cool, so we get the total number of bytes on the disk, the amount that's used, and the amount that's free. We can calculate the percentage of free disk space by dividing the number of bytes free by the total and multiplying that by 100. Alright, but what about CPU usage? For this, we can use another module called psutil. This includes a CPU percent function that returns a number showing how much of the CPU is being used. The amount of CPU used at each instant can change a lot, since processes are starting and finishing all the time. So, this function receives an interval of seconds and returns an average percentage of usage in that interval. Let's try it out. We'll start by importing the psutil module. Then, call the CPU percent function with 0.1 seconds. When we're using the interactive interpreter, we can use the arrows in our keyboard to get back the lines that we wrote before. So, using the up arrow, let's execute the same line a few times. As you can see, this can vary a lot. Let's try it with 0.5 seconds. See how it's taking longer to finish than previous calls, but the numbers are more similar to each other? That's because the function needs to wait for the given time to calculate the average. Okay, so we've done a bunch of research. Now we can write our health checking script. We'll kick off with a script that'll do 2 health checks. First, we'll set our script to use the Python interpreter with the shebang. We know that we'll use shutil and psutil, so let's import those 2 modules. Let's first define a check disk usage function that will receive a disk to check and return true if there's more than 20% free, or false if it's less. And now, let's write another function called check CPU usage. In this case, we'll check the usage for a whole second. We'll say the machine is healthy if the CPU usage is less than 75%. Great, we have our 2 functions. Let's now add the main body of our script where we'll check if either of those 2 functions returns false. So here, we're just printing a message that the user will see. We'll improve on the script later on once we've learned better ways of notifying our system administrators. We're almost done. Let's save our script, make it executable, and run it. So there you have it. Everything's okay, which seems like a great point to wrap up this exercise. All along this course, we'll explore practical automation examples which you'll be able to apply in your job. And as we talk about the additional functionality available, we'll be able to extend our automation knowledge to more and more areas. So how are you feeling? Some of this stuff is a little tricky, and learning about automation calls for a little bit of manual work. The irony isn't lost on us. So roll up your sleeves and practice these scripts on your computer. Also, feel free to rewind and rewatch if you felt a little lost anywhere.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.